Very difficult Wednesday. Next becomes very slow. I think this time, peak time. So let us study origin of spectral lines. And I think you already studied the spectral lines in hydrogen spectrum in chemistry. Lyman, Balmer, Paschen, Brackett, Fund. These are the spectral series of spectral lines observed in hydrogen atom. Then you can see the nucleus here in atom, and the electrons are revolving in different orbits. That orbits are shown, and orbits, electrons have definite amount of energy. They are moving in stationary orbit according to Bohr's quantum model. Electrons are revolving in stationary orbits. They have definite amount of energy, and energy also we have calculated, derived the expression. And when an electron jump from higher energy level to lower energy level, what happened? When an electron jump from higher energy level to lower energy level, what happened? Ghanasham, what happened? Ghanasham. Ghanasham. When an electron jump from higher energy level to lower energy level, what happened? What happened when an electron jump from higher energy level to lower energy level?
Release energy.
Very good. They release energy. Okay. And that energy formula, what is the formula for energy of radiation emitted? Achmala, what is the formula of energy radiated? E equal to formula. Ajmala is there? Aishwarya, what is the formula for energy radiated?
E equal to h nu.
Very good. E equal to h nu. Energy radiated E equal to h nu. Where h is the Planck's constant and nu is the frequency of the radiation emitted. And here I have shown two levels, E2 and E1. And electron is jumping from E2 to E1. Then this is shown here. Energy emitted h nu, photon, electromagnetic radiation of energy h nu is emitted. And that energy, how will you calculate energy? From which level to which level electron jumped? You find the difference of that energies. That will be the energy of the photon emitted from it. So that is what is calculated here. Here E1 and E2 are the two levels. E1 is the energy level which is near to the nucleus. So energy will be less here. We know first orbit minus 13.6 eV is the energy. Second orbit it will be minus 13.6 by 2 square. Minus 13.6 by 2 square, that is the energy. And first we are finding the general equation. Nala is coming on. Okay, waiting, it is not showing here. Okay. So here electron jump from an outer to an inner orbit. The energy of the radiation emitted according to Bohr's third postulate is h nu equal to E2 minus E1. And we already got the formula for energy of different energy of electron in different orbits. So in n1th orbit and 2 orbit, we already know it is minus sign. So you should know this equation. Minus 2 pi square mk square z square e raised to 4 by n2 square h square. That is E2. And what is E1? In the place of n2, you have to write n1. Understand? That is the only difference. And minus comes. Minus, again, energy is also having one minus. So minus it becomes plus. That's why we got plus here. Actually, energies are negative. Only at infinity, zero energy. All other levels, energy is negative. So constant part is taken outside, and then inside what we get, positive value we are writing first 1 by n1 square minus here 1 by n2 square is written. Then this CH is taken to the denominator because we have to find the wavelength. So CH is taken to the denominator of right side. So what we get? 2 pi square mk square is e raised to 4 z square by ch cube into 1 by n1 square minus 1 by n2 square. That is 1 by lambda. It is also known as wave number. So that 2 pi square mk square z square e raised to 4 by ch cube into 1 by n1 square minus 1 by n2 square. So this energy formula and all you have to by heart. Otherwise it will be difficult to derive. For this, if this question comes, if we go for deriving the total energy, it will take more time. So if you know this final expression, you can easily write it here, substitute it here. So better study the final expressions by heart. Then that constant part value, 2 pi square mk square e raised to 4 by ch cube. That's a constant part. It is known as Rydberg constant, named after the scientist, Rydberg constant. Rydberg is the name of the scientist. And its value also 1.097 into 10 raised to 7 per meter. That is Rydberg constant value. So for doing problems and all, you have to remember this because Rydberg constant value they will be giving to you, or you should know that 1.097 into 10 raised to 7 Rydberg constant into Z square. Depending upon the element, Z atomic number will change. For hydrogen atom, we can take 1. We are finding the equations for hydrogen atom, but in problems and all, they will give a lithium atom or sodium atom, like that they will give. So you have to write the atomic number of that element. So R into Z square into 1 by n1 square minus 1 by n2 square. So this is the final formula. Nu bar, wave number, nu bar equal to R into 1 by n1 square minus 1 by n2 square. This is also known as Rydberg formula for the spectrum of hydrogen atom. So we have studied a very important formula, Rydberg formula. Next, Bohr's explanation of spectral series of hydrogen atom. So we have seen different series of spectral lines: Lyman, Balmer, Paschen, Brackett, Fund. 5 series of spectral lines are observed for hydrogen atom, and this is the explanation for that. Lyman, name of the scientist. Lyman observed this series. Bohr postulated that Lyman series is obtained when electron jump to the first orbit, n equal to 1. I will show the diagram. Yes. This is the energy level diagram. And see, so energy level diagram, you can see electron jumping from, these are the higher energy level. Minus 13.6 is the ground state energy. All you should know this. Ground state means n equal to 1 for doing problems. This is a must know this. Children usually make mistake. Ground state n equal to 1. So first excited state, what is n? First excited state n equal to 2. Ground state is n equal to 1. So energy in the ground state is minus 13.6 eV, minus 13.6 eV. Then first excited state, that is n equal to 2. Well, how you are getting this value minus 3.4 eV? Anyone? Nandana, how you are getting this value? First excited state energy.
So minus 13.6 EV by 2 square.
Very good. By 2 square. Okay. Mute your mic. Okay. Then see, by first excited, the second excited state n equal to 3. So we have to minus 13.6 by n square. Minus 13.6 by n square upon 3 square. So we get the energy here. Like that we are calculating the energy. And when an electron jump from first excited state to the ground state, second excited state to the ground state, it releases energy. and one radiation is gone, and we got the wavelength corresponding to that. It will have energy hc by lambda, it will have wavelength lambda. So like that, when an electron jump from higher energy level to the ground state, we get Lyman series. A series of spectral lines are observed when an electron jump from other states to other excited states to ground state. That is Lyman series. Then Balmer series. What is Balmer series? When electron jump from higher energy state, like excited states, to n equal to 2. First excited state, n equal to 2. So Balmer series is observed when electron jump from higher energy level to n equal to 2. All this you should remember. N equal to 2. Balmer series, and it is invisible region. And then this is first excited state, so this will be second excited state, n equal to 3. So we get Paschen series. So we can substitute that in that formula. Lyman series. So this is the formula. Nu bar equal to wave number. Nu bar equal to r into 1 by first ground state, n equal to 1, ground state. So 1 square minus 1 by k square. What is k? K is other than 1. All other levels other than 1. What is other than 1? 2, 3, 4, etc. K equal to 2, 3, 4, etc. So we get a series of spectral lines corresponding to each transmission. We get one spectral line. This is in ultraviolet region. Ultraviolet region. So what is by Lyman series? When electron jump from higher energy level to ground state, that is n equal to 1. Okay, we get a series of spectral lines that is known as Lyman series. It lie in the ultraviolet region. The region also you should remember. The participants are waiting. Then Balmer series. I'll ask to Adityan. I will Adityan. Balmer series. Can you tell the formula? Nu bar equal to Balmer series. ഒരെണ്ണം പഠിച്ചു കഴിഞ്ഞാൽ ബാക്കി എല്ലാം പറയാൻ പറ്റും. പിന്നെ കഷ്ടപ്പെട്ട് നമ്മളത് പഠിക്കേണ്ടായില്ല, അത് നോക്കിയിട്ട് പറഞ്ഞാൽ മതി. Balmer series. Adityan. Nu bar equal to Adityan. Are you there? No. Ismail, tell. Ismail. Ismail.
Teacher.
Ismail, tell the formula for Balmer series. Nu bar equal to R into എന്ത് വരും? R into electrons are jumping from higher energy level to which level? Nowadays Ismail is not at all answering anything. Why? What happened, Ismail?
Second level അല്ലേ teacher?
1 by
Second level.
സെക്കൻഡ്. അപ്പൊ 1 സ്ക്വയർ എന്നുള്ളടത്ത് എന്ത് എഴുതണം? 1 സ്ക്വയർ എന്നുള്ളടത്ത് എന്ത് എഴുതണം എന്ന് പറ. അറിയില്ല? ഇൻ ദ പ്ലേസ് ഓഫ് അതായത് 4 തന്നെ 2 സ്ക്വയർ. ഓക്കെ, 2 സ്ക്വയർ കേട്ടോ. ഓക്കെ, 2 square minus 1 by k square. K, what will be k, Ismail? What will be k? Other than 2. Which is other than 2?
3, 4, 5.
Yes, 3, 4, 5, etc. Okay. Lyman, Balmer. Balmer lies in which region? Anyone? Adityan, waiting. Okay, I'll do this. Okay, Balmer series observed in visible region. So Balmer series is obtained when electron jump to the second orbit, n1 equal to 2, from any outer orbit, n2 equal to 3, 4, 5, etc. And wave numbers u bar equal to r into 1 by 2 square minus 1 by k square. Passion series ചോദിക്കട്ടെ. Passion series. Akshaya, tell passion series equation. Akshaya. Passion series equation, tell. U bar equal to Akshaya. Akshaya, അവര് ശബ്ദമൊന്നും കേൾക്കുന്നില്ല. Lemya, can you tell what is new bar? Balmer കഴിഞ്ഞു. Alignment Balmer കഴിഞ്ഞു. ഇനി passion series ആണ്. What is the equation? New bar equal to ഏത് ലെവലിലേക്കാണ് ഇലക്ട്രോൺ ജമ്പ് ചെയ്യുന്നത്? n equal to mm. Remisa is there? Remisa? ഇല്ല. സേത് പാർവതി? സേത് പാർവതി? Badra, tell. Badra. New bar equal to R into
1 by 3 square minus 1 by k square.
Where k equal to?
K equal to 4, 5, 6.
Yes, very good. 4, 5, 6, etc. And it is in infrared region. New wavelengths lie in infrared region. Okay, ബാക്കിയുള്ളതൊക്കെ ഇൻഫ്രാറെഡ് ആണ് കേട്ടോ. അപ്പോൾ അൾട്രാവയലറ്റ് ലൈനാണ്. പിന്നെ ബാൽമർ ഈസ് ഇൻ വിസിബിൾ റീജിയൻ. അതർ സീരീസ് ആർ ഇൻ ഇൻഫ്രാറെഡ്, ഫാർ ഇൻഫ്രാറെഡ് എന്ന് പറഞ്ഞു പോകും. അപ്പോൾ പാഷൻ ഇനി നമുക്ക് എളുപ്പമാണ് എഴുതാനായിട്ട്. പാഷൻ സീരീസ് വിനോ, then bracket series will be 1 by 4 square minus 1 by k square, and fund series will be 1 by 5 square minus 1 by k square. So if you study one formula, you can write other formulas also. Doing problems, it is very, very important. The next is energy level diagram. How to draw the energy level diagram? That is what I have shown. The total energy of the electron in an orbit is given by the formula minus 13.6 by n square eV. Put n equal to 1, 2, 3. We get first orbit, ground state, n equal to 1. First excited state, n equal to 2. Second excited state, n equal to 3. Writing that, we get the energy in different orbits. So, n equal to 1, we get ground state. Always remember that n equal to 1. First excited state, alla. അതാണ് തെറ്റിക്കാൻ സാധ്യതയുണ്ട്. സോ ഗ്രൗണ്ട് സ്റ്റേറ്റ് n equal to 1 വെച്ചാൽ ഗ്രൗണ്ട് സ്റ്റേറ്റ് ആണെന്ന് ഓർക്കണം. n equal to 1. അത് 1 കേൾക്കുമ്പോൾ ചിലപ്പോൾ ഫസ്റ്റ് എക്സൈറ്റഡ് സ്റ്റേറ്റ് ആണെന്ന് കൺഫ്യൂഷൻ വരും. തെറ്റിക്കരുത്. n equal to 1 എന്ന് പറയുന്നത് ഗ്രൗണ്ട് സ്റ്റേറ്റ് ആണ്. ഗ്രൗണ്ട് സ്റ്റേറ്റ് എനർജി E1 minus 13.6 by 1 square minus 13.6 EV. E2 first excited state n equal to 2 minus 3.4. E3 minus 13.6 by 3 square. That answer is minus 1.51. So like that you can calculate energy in different orbits. As n increases, energy becomes less negative. At infinity, energy becomes 0. Positive. And why this energy is negative? Because electrons are bound to the nucleus. That's why negative energy is there. And the energy level diagram means this is the energy level diagram. Here what we can see different horizontal lines are drawn on a particular scale. And these lines represent energy of the electron, energy levels. And the ground state is written n equal to 1, and we have written the value minus 13.6 eV. N equal to 2, we got the energy minus 3.4. N equal to 3, we got minus 1.5. Like that we are getting the energy. This is the energy level diagram. And this is the spectral series. Series of spectral lines observed. Limitations of Bohr theory. What are the limitations of Bohr theory? You have studied that. It is applicable only to hydrogenic atoms. That means atomic number 1. This theory is applicable only to simplest atom like hydrogen with Z equal to 1. Z equal to 1. അത് മാത്രമേ എക്സ്പ്ലെയിൻ ചെയ്യാൻ പറ്റത്തുള്ളൂ. അതൊരു limitation. That is the limitation. According to Bohr theory, both circular and elliptical orbits are possible, but it does not give any clear idea why circular orbits are taken. So there is no explanation for why circular orbits are taken, not the elliptical orbit. So that is all limitation. Then Bohr's theory does not explain fine structure of spectral lines even in hydrogen atom. Even in the case of hydrogen atom, the fine structure of spectral lines are not explained. Then this theory does not predict the intensity of lines. The different intensity are observed. That for that also no explanation is given. This theory is applicable. Then it is applicable only to simplest atom like hydrogen, then doubly ionized helium, like some elements. The atomic number 1 only. Like that examples are there. Then de Broglie's explanation of Bohr's second postulate of quantization. For that I will show you a video. That then it will be very interesting to you. De Broglie's explanation of Bohr's second postulate. And let me check. Is it there indeed? Okay. This I will show you that. Random. It is not moving. No, it's not moving. Okay. So de Broglie.
Is a ruler 2 meters from the center of the seesaw.
De Broglie's explanation of Bohr's second postulate. Okay, this one. If you are not hearing, you please tell me. Okay. That is sad. Children, if you are not hearing,
De
please tell me.
Broglie's explanation of Bohr's second postulate of quantization. It is very difficult to explain the Bohr's second postulate. It states that an electron can revolve only in those orbits for which its orbital angular momentum is an integral multiple of h by 2 pi times when n equals to 1, 2, 3, and so on. The quantization is why should the angular momentum can have only those values that are integral multiple of h by 2 pi. The question was explained by the French physicist Lars de Broglie in 1923, 10 years after Bohr's proposal. According to de Broglie's hypothesis, all material particles, such as electrons, also have a wave nature. C.J. Davison and L.H. Germer later experimentally verified the wave nature of electrons in 1927. De Broglie argued that the electron in its circular orbit must be seen as a particle wave. In analogy to waves traveling on a string, particle waves can lead to standing waves under resonant conditions. We know that when a string is plucked, a vast number of wavelengths are excited. However, only those wavelengths survive which have notes at the ends and form the standing wave in a string. In a string, standing waves are formed when the total distance traveled by a wave down the string and back is one wavelength, two wavelengths, or any integral number of wavelengths. Waves with other wavelengths interfere with themselves upon reflection and their amplitudes quickly drop to zero. For an electron moving its nth circular orbit of radius Rn, the total distance is the circumference of the orbit, 2 pi Rn. A standing wave is shown on a circular orbit where 4 de Broglie wavelengths fit into circumference of the orbit. 2 pi Rn equals to m lambda, equation 1. N equals to 1, 2, 3, so on. Figure illustrates a standing particle wave or a circular orbit for n equals to 4. That is 2 pi Rn equals to 4 lambda, where lambda is a de Broglie's wavelength of the electron moving in nth orbit. And we know that lambda equals to h by p, where p is the momentum. If the speed of the electron is much less than the speed of the light, then momentum p equals to mvn. Therefore, lambda equals to h by p equals to h by mvn. And we know that 2 pi Rn equals to m lambda equals to n into h by mvn.
Okay, children. This is actually what we have to study. De Broglie's explanation of Bohr's second postulate. What is Bohr's second postulate? MVR, angular momentum, MVR equal to NH by 2 pi. That is Bohr, an integral multiple of h by 2 pi. That is Bohr's second postulate. What is Bohr's second postulate? Everybody should know that. What is second postulate? MVR, angular momentum, MVR is integral multiple of h by 2. Why always integral multiple? We are not taking half into h by 2 pi or 3.5 into h by 2 pi. Like that we are not taking. Integers, integral number, 1 times, 2 times, 3 times, like that only we are taking. Integral multiple of h by 2 pi. Angular momentum of the electron in an orbit is integral multiple of h by 2 pi. So that for that, this is the explanation given. When an electron, see this is the orbit, circular orbit. When an electron moves in circular orbit, it moves as waves that we have studied. Particle is having dual nature. Particle is having dual nature. Electron is a particle. So when it moves, it is having wave nature. And that is dual nature we have studied that. particle electron is having dual nature when it moves. And when it moves, see, the length is fixed. The circumference is fixed, that is 2 pi r. When it moves on around this or around this nucleus in the circular orbit, it moves in the form of waves. And this, see, we can, these are standing waves are formed. Standing waves will have nodes. Nodes means no vibration here, and nodes, antinodes, like that. And difference between, see, this is one wavelength, and one wave is this, one crest, one trough. That will constitute one wave. The distance between these two positions, this is one crest and one trough. Both together make one wave. So wavelength will be either distance between two crests, or distance between two troughs, or distance between two consecutive points which are in the same state of vibration, like that. So in state of vibration means here, see, this wave you can consider one wave. So this is the wavelength, distance between two crests, or distance between two troughs, all are wavelength, same. So I will tell you once again, when electron move in circular orbit, it move in the form of waves, okay, and it will have wavelength. When there is a wave, there is wavelength. So electron also will have wavelength, and that when it move in circular orbit, it form standing waves. Standing waves in nodes, nodes, between two nodes. But then node, electron is moving. So it will have nodes, standing waves will have nodes. And here, this is, suppose this is the fourth orbit. Fourth orbit. So total circumference is 2 pi r. 2 pi r equal to 4 lambda, 4 wavelength. Fourth orbit. N equal to 4 I came out 4 wavelength. And when n equal to 5 5 wavelength. 2 pi r equal to 5 lambda. 2 pi r എന്നുള്ളത് 5 കൊടുക്കണം. 2 pi r equal to 5 lambda. അപ്പം nth orbit ആണെങ്കിലോ 2 pi r equal to n lambda നിൽക്കണം. ഓക്കെ, അപ്പോൾ 2 pi r equal to n lambda, that is the first equation, where n equal to 1, 2, 3, 4. So, അപ്പോൾ fourth orbit 2 pi r equal to, this is an example given, 2 pi r equal to 4 lambda. And we know, we have already studied de Broglie wavelength, lambda equal to h by p. What is P? P is the momentum. What is the equation for momentum? Momentum, you see, in light, see, when it moves waves, light waves, electromagnetic waves, we have taken momentum is mass into velocity of light taken. But here it is electron. Electron velocity is less than that. We have already calculated velocity of electron. 1 by 137th that of the velocity of light only it is having. So, momentum equal to mass into velocity. We are not taking c here because they are not having the velocity of light. Momentum equal to mass into velocity of electron. So, lambda equal to h by p, and p is substituted h by mv, and we know 2 pi r n equal to n lambda, n into lambda, this value you have to write here, nh by mv. And the next step, it is given in another video, that's why I have stopped this. So mv take to this side, mv take to this side, left side, 2 pi take to right side, denominator. Appa mvrn equal to nh by 2 pi, mvrn, mvnrn. mvr means what? What is mvr? Question. Arunjit, what is mvr? Arunjit. Arunjit, what is mvr? Answer. Krishnanunni, what is mvr? What is mvr? Tell.
Angular momentum.
Very good. Angular momentum. Angular mvr. Mv take to the left side and 2 pi take to the right side. What is the equation we are getting? Shanuni?
MVR equal to NH by 2.
Correct. MVR equal to NH by 2 pi. That is Bohr's second postulate. So, de Broglie explained Bohr's second postulate. Okay. So, that is de Broglie's explanation. I think you understood. Without the figure, it would have been very difficult to explain. So, it becomes easy for now. So, electron move in only 5 minutes more. Electron move in orbit. It moves as waves and it forms stationary waves. And for stationary waves, we know 2 pi rn equal to n lambda. That is the equation. Therefore, lambda, we can determine lambda equal to h by p equal to mv substituted. Then that is substituted in the formula lambda h by mvn. Then mv take to left side. Then we get mvr equal to nh by 2. Only that. Usually ask us a 2-mark question. Okay. So we can move to our page. Angular moment. So with that, I think we have completed that chapter. The Broglie's explanation. Oh no, one more point. Excitation potential. Maybe. Excitation and ionization potential are two more small points. Wow. Do you have any idea about that excitation and ionization potential? What is excitation potential, children? Excitation energy. Anybody know? Excitation energy. What is meant by exciting an atom? What is meant by exciting an atom? I will ask to Abhinand, what is meant by exciting an atom? Exciting an electron. What's meant by that? Abhinand?
Yes, teacher.
What is meant by exciting? Excitation potential. Exciting means what? Exciting an electron from. What is meant by that?
Read the teacher.
Giving energy to the electron so that it will jump from lower energy level to higher energy level. Like inner orbit to outer orbit. That's excitation. But when you get an atom get energy, electron jump from lower energy level to higher energy level. Inner orbit to outer orbit. അതിനാണ് നമ്മൾ എക്സൈറ്റേഷൻ എന്ന് പറയുന്നത്. അതിന് നമ്മൾ എത്ര പൊട്ടൻഷ്യൽ അപ്ലൈ ചെയ്യണമെന്ന് വോൾട്ടേജ് ആണ് അയണൈസേഷൻ excitation potential. The process in which absorption of energy by an electron takes place and the electron jump from an inner orbit to some outer orbit is called excitation. And the minimum accelerating potential which provides an electron energy sufficient to jump from innermost orbit, that is the ground state, to one of the outer orbit. Outer orbit may be first excited state, second excited state, third excited state, any level it can be. So, from inner orbit to outer orbit, that's all. The energy required for the electron to jump from inner orbit to outer orbit, an excitation. Then we can excitation energy and excitation potential. For example, we know energy as the first ground state. Ground state energy is E1 equal to minus 13.6 eV. And the first excited state energy is this divided by 2 square. We get minus 3.4 eV. This is first excited state. Second excited state minus 1.51 eV, like that. And what is the energy required for the electron to jump from ground state to first excited state? Ground state to first excited state jump ചെയ്യാൻ എത്ര എനർജി വേണം? ഇത് minus 13.6 ഫസ്റ്റ്, അതാണ് ഏറ്റവും കുറവ്. ഇത് കൂടുതലാണ്. അപ്പൊ ഇതിന്റെ ഡിഫറൻസ് കാണണം. അതായത് -3.4 അതല്ലേ കൂടുതൽ, -13.6 ചെയ്യാം. -3.4 മൈനസ് വരുമ്പോൾ എന്താവും, പ്ലസ് 13.6 വരും. അപ്പൊ 10.2 EV വരും എനർജി. 10.2 EV വരും. നോക്കിയേ, -3.4 -13.6 equal to 10.2 EV. അപ്പൊ കറസ്പോണ്ടിങ് ഇതാണ് എനർജി റിക്വയർഡ് ഫോർ ദ ഇലക്ട്രോൺ